Alrighty, everyone. Hello, welcome to Improving's Lunch and Learn. Today, we're going to enjoy a presentation by Improving's Technical Director, Michael Slater. He is going to present about machine learning. Before we begin, please look down at your screens. At the bottom, near the center, you're going to see a Q&A button. Go ahead and type your questions in there. I'll be responsible for finding an appropriate time to ask them during Michael's presentation. He will be answering during the presentation rather than holding for the end, so ask your question anytime. And with that, please take it away, Michael.
All right, thank you. And you can see everything okay?
You are not sharing your screen.
Oh, it did not keep it over. Huh. One moment. Now I have to figure out where that is.
Apologize, I should have warned you about that. It does reset screen share.
There we go. All right.
Yes, sir. We're looking at your slides.
Well, thank you, everyone. Welcome to my talk on AI and machine learning, man versus the machine. I'm going to quickly go over an overview of machine learning, and then we're going to jump right into Azure Machine Learning Studio and develop a model. A little bit about me. I'm a technical director here at Improving. What that means at a high level is I meet with businesses doing exciting work, and I figure out what problems they want to solve with software. So we're a group of professional software consultants. We also do a variety of other IT consulting. Please connect with me on LinkedIn if you want to reach out about this presentation or improving in general. A little bit about my hobbies. I'm big with my family. My wife and son live here in Houston, Texas, and we do a lot of barbecuing, cycling, and an avid video gamer. So if you want to connect with me about any of those things, feel free. Just getting started on AI. I like to present this kind of slide because a lot of people believe that the current state of artificial intelligence is like the Terminator over there on the left. That's going to be some mean killing machine. But in reality, AI is a lot more like Bender. It's kind of silly and stupid and can hardly follow simple instructions sometimes. And we'll get into a little bit of that. Of course, there's very advanced AI systems out there now today. But it takes a lot of work to build them. A little bit about the difference between artificial intelligence and machine learning. And I'm going to start with actually the bottom here. Machine learning takes data and answers to create rules. And this is at least supervised machine learning. But what that means is that for a machine to learn, you have to give it data as well as the answers to the problem you're trying to solve from that data. And the machine learning algorithm will develop the rules set to predict future answers from future data. Now, AI flips that a little bit on its head. It takes rules and data, and it gives you answers. So in a way, you could see artificial intelligence as employing the use of a machine learning model, or in reality, lots of machine learning algorithms, as well as lots of other systems and input and rule sets, as well as the data to give you answers, right? And that's a way you can look at the difference at a very high level. So today we're going to be talking about model development, and I'll be developing a model in front of you in a classical machine learning model. So talking a little bit about the steps, and you're going to see me go through these steps, is the first steps is gathering and preparing data. Right. So this is where in the model development phase, you want to gather and prepare the data that you're going to be able to use, not only to train the machine learning model, but it has to be the same data that you're going to be able to use to predict answers from. And again, we're talking about supervised machine learning here. Right. So the data has got to look like what it will, let's say, in production when you're using the machine learning model. So it needs to be the same type of data, the same field, same parameters, etc. Right. And once we go through that preparation data, we're going to train the model. Right. And this is where we, essentially call a function saying, hey, machine learning model, given all this training data, train yourself. And that's when it goes through that cycle of computation training. Right. Sometimes this is what you'll hear where, artificial intelligence scientists or machine learning engineers need like lots of GPUs or, massive computational networks to train models. The type of classical machine learning model that I'm going to show you actually doesn't even need a GPU. It can be trained on any local computer. That's because it doesn't utilize GPUs. It's not a neural network or any of those other advanced machine learning models. But then after that, we're going to test the model. So we train a model and then we're going to test the model. And what we mean by test is, one, we're going to see, of course, if it works, but also we're going to see if, it gives accurate results, right? So, we've trained it with a certain amount of data, but we've also withheld a little bit of our training data with the answers to see, hey, does it give us predictions that we think are accurate, right? And we're going to go through this step of testing that. I'm going to skip update weights and biases. That's more for neural networks. But the hyperparameter adjustment here, that definitely happens in classic machine learning model development, and we're going to do it today, right? And you may adjust some hyperparameters and retrain your model, kind of like tweaking these settings, let's call it, of a machine learning algorithm to perform a little bit better based on your type of data, right? And that is the full life cycle kind of training a model, right? And so you can see here we have the training cycle, the model cycle, the full life cycle. And you may do this, for a given problem that you're solving. You may do it once per data set. You may have to do this once a year, once a month, once a week, right? And you start thinking about the systems you have to create to help even automate this part of machine learning. And the last part we'll talk about here before we jump into the hands-on part is classification. And I'm mostly talking about classification because that is what we're going to do today, right? So classification is a type of supervised machine learning algorithm training. It's where we categorize data into a set of classes. One way to think about this is if you have an email message, a classification structure that could be done is this email spam or not spam, right? And all the email providers out there today have, massive rule sets, probably almost definitely use machine learning in some way to help determine if every email, right, is spam or not spam. In fact, some of them even go a step further, like with focused inbox or priority email, trying to determine, is this email even important or kind of not important, right? And they'll, these systems have gotten even more advanced between spam and not spam. And so in this supervised classification, we're really just categorizing a set of inputs into one category from a list of categories. All right. A couple terminology here. So, the classifier is the algorithm. The classification model is the machine learning model itself. A feature, and sometimes these are called parameters, but a feature is a property of input. Right. Binary classification is when you only have, two categories like yes or no, spam, not spam. Whereas multi-class classification is 3 or more. Right. And there's actually algorithms that are really good at only 2. And then, they don't work well if there's 3 or more. So it can tie into your algorithm choice. Right. And I'm not going to go on to these other slides because this is a hands-on talk. So we're going to go into model building. So here I am in Microsoft's Azure Machine Learning Studio. I use this because I don't want to have anything installed locally on my machines. So I usually just spin up a VM with my Jupyter Notebook in Azure, and it lets me, do work kind of anywhere. It's really nice and convenient. I'm going to go ahead and click here in data. So I've uploaded my data set, and it's called loan modeling. We're going to model a data set from Kaggle, which is a data science data platform, which basically determines whether or not we're going to give people loans. And the first thing I'm going to do is kick off the machine that I'm going to compete against. Right. So I go into automated ML. Automated ML is kind of Azure's let me find a machine learning algorithm for you type of approach, right? It's like model development as a service, you could even call it. So given a data set, it will actually try and find a reasonably well-performing model and train it all on its own, right? And all I have to do is provide the data set. I'm going to provide a version of the data set that doesn't have identifiers. that I've given there. Right. So I'm going to do improving lunch. Oh, I'm going to create a new experiment. Right. Loan modeling lunch and learn. Cool. So the target column is the column I'm going to predict. And as I mentioned, this is about personal loans. So I'm going to pick personal loan, right? And the integers because it's a 0 or 1 for yes or no. I'm going to pick a compute instance. And I have a 4-core, 14 gigabyte RAM compute running. Like I said, it doesn't have a GPU because for the type of machine learning algorithms we're doing, they don't need a GPU. Otherwise, I might, have to pick something a little more expensive in Azure, which I usually, avoid unless I'm doing very important work. So I'm going to hit next here. So I'm not hitting this deep learning checkbox because as I mentioned, we're going to do classical machine learning algorithms. Go and hit next. Validation type, it's going to be auto. Most likely it's going to choose k-fold cross validation. In fact, we can go and pick it. I'm going to decrease this a little bit just to make sure it runs, but this is the number of validations it will do. And then it's not going to need a test data set because k-fold cross validation does not need test data. It actually, in a cool algorithmic way, does a test data all on its own. And I'm creating the new ML job, and that's it. It's running. So right now, Azure's kind of automated ML framework is running on a compute instance I provisioned, and it's basically going through a loop of every algorithm it's programmed with to say, hey, given this input, just throw it through this algorithm and see if it works, so in a way, it's very simple, but it's also really cool because it's going to test like 50 algorithms for me. And in a way, this is a good way to maybe narrow down what a good algorithm is for this data set. You may not use the model it generates out of the box in a production system, but so I'm going to go ahead and open my own notebook. I'm going to go ahead and here, I'm going to clear all the outputs from my testing earlier. So let's do cell operations, clear all outputs. There we go. So I'm opening a machine learning model that, of course, I've already written all the code for. I wasn't going to risk like actually coding in front of you. That could be very dangerous. But this is a model I developed from the Kaggle data set. And so I'm going to start with a bunch of Python imports here. Let me zoom in my screen, actually. There we go. And go ahead and there we go. All right. So I'm importing pandas, NumPy, matplotlib. Pandas and NumPy are, some computational and data manipulation libraries. Matplotlib is actually going to let me graph things within this notebook. And Seaborn makes the graphs pretty. Now this import's very important. sklearn, that is the kind of the Python data science toolkit I'm using, sklearn. And if we Google that, actually, we'll go to right here, scikit-learn. You can, learn and look up the models I'm even using. And here's classification, right? So we're using something in here. In fact, I can go and find it. We're going to use a decision tree classification. So I'm essentially following this tutorial right here. Because we're importing a tree, because we're going to do a decision tree. I'm also importing a few specific functions, train, test, split, which is going to help me develop the model, as well as grid search, which is an optimization function. All right, let's go ahead and run this. Take a minute to get started. Cool, and it's ran, so we're up and running. I'm going to import my data set. This is just the code it takes to import from a data set I've uploaded into Azure's Machine Learning Studio. Now let's talk about the goal for a minute. The goal is, as a data scientist, I'm going to build a model that will help identify potential customers who have a higher probability of obtaining a loan. And a little bit more that I should have written here maybe is that I'm going to give this model to the marketing department. So that marketing department will know who to market to of their internal customers for some internal marketing to say, hey, these customers, if you market to them, are more likely to obtain a loan than if you just marketed to everyone at random, right? And there's always a cost to marketing. So in a way, it's good to optimize that, cost of marketing dollars. Say, hey, let's only market to people who have a higher probability of obtaining a loan. So you can see the real business objective, the real business value to this one-off data science problem I'm going to solve, right? And one of my objectives there is which variables are more significant. So I'm going to even be able to tell the marketing department, hey, these specific attributes or parameters, features of customers are really the differentiators in targeting them, right? Looking at our data dictionary, and I have a link here, kaggle.com, to this data set. So it's a public data set available to anyone on the internet. But in my data dictionary, I have age of the customer, experience, number of years of professional experience, their annual income in thousands, zip code, which is their home address zip code, the size of their family, the average credit card spending revolving balance in thousands of dollars. I have a education level, value of house mortgage, if any. That if any part's a little important to note. Whether or not they have a security CD account, if they do online banking, and if they have a credit card by this bank. And of course, the last attribute is the answer from a previous marketing campaign. The target, did this customer with this profile accept a personal loan offered in the last marketing campaign? And that's where the supervised learning part of this is going to come in. We already have the answer to the previous campaign that is going to inform our predictions for the next campaign. So let's go and look at a sample 5 random rows of this data set. And here I can see all the parameters I talked about, and just kind of an off the glance look at them. One thing I'm going to note here is, I see 3 years of experience, like I also see 34 years experience. So we have a pretty wide range there. We have a wide range of income in just these samples. The zip codes are your standard 5 zip codes. I'm also seeing here mortgage is 0. So we're going to maybe assume those are renters and they just don't have a mortgage, or they paid off their mortgage and they own their home outright. We don't really know. And this kind of speaks to the unknown in data sets a little bit. There's no way to know if we don't have the data, so we have to make do with what we have. And that's always something to consider in any data science, data analytics type problem, is what you know and what you don't know, the limitations of your data, right? And we can see that there's these 0 or 1 things for our personal loan, security, CD, online, and credit card. So I'm going to go ahead and call a function called info. This is really useful because it let me see how many rows I have and null values. I don't have to worry about today. As you can see, null values, I have 5,000 rows in all categories, and they're all non-null. That means I have answers in all of them. So I don't have to worry about how any missing values are going to affect this particular algorithm. But for future algorithms, this is actually kind of a critical step. But I had to choose what types of data preparation I was going to show off today. So I chose a data set without that problem. But normally, if you have null values, like a very simple objective would be to choose like the mean or median value in that data set. Would be a simplistic way to fill null values, because a lot of algorithms do not accept nulls. So you would have to fill those values in with placeholders, or choose an algorithm that can accept nulls, right? So already you're starting to look at attributes of machine learning algorithm selection. So looking at some basic data cleanup steps, I'm looking for any duplicated or null values. Again, I'm going to see no duplicates and no nulls. Up here, if you notice, there's an ID column that really matches the row number. That has no, bearing or significance in the machine learning algorithm development. So I'm going to just immediately drop that from my data set. I don't need it. I also, like every programmer out there, I don't like spaces in my variable names or in, spaces in general. So I'm going to remove spaces from my columns. It makes some of the programming ahead easier, so I don't have to escape those spaces. Going to print out the value counts of some of these categorical type inputs. So family, it looks like I have 4 values. Education, 3. Securities, CD, online, and credit card, I have 2 values each. And then in experience, I have a lot of values. right? Actually, even noting I have some negative values there. We're gonna have to talk about that. And in zip code, I have 467 unique values. That's going to be way too many. So we're going to have to do something about zip code too. It's not even printing all of them out on the screen for me. I'm going to run a function in called describe. And this is in the pandas library because I'm operating on a pandas data frame. This is going to describe basic statistical information over all the numeric features in my data set. So in age, for example, I see the mean age, the average age is 45. The minimum is 23, so that's my youngest person in the data set. And the maximum is 67, that's my oldest person in the data set. I can have, experience. Again, I see -3 experience. I'm starting to think that's a real problem. There should not be negative experience for anyone. I can't think of a good reason. And maximum is 43. That kind of makes sense if you think 23 plus 43 years is going to be, 66, which kind of, aligns with our max age. So the max makes sense, but the min does not. And this is where you start thinking about, as you're analyzing your initial data, reasons the data may have issues. So if you've ever worked in any business or organization, in IT and data management, that oftentimes data is not perfect, right? And sometimes we just live with imperfect data every day, but sometimes we have to know that we're going to need to do something about it, right? And that's what we're going to talk about, right? And so I've given my initial analysis of data values here, and I've identified 2 issues. Experience of -3 seems like a data entry error of some way. It needs investigation. And I have another issue, and this is more of a back-end issue. So I have kind of like a data quality issue with my business, but then I have like a data issue for the algorithm, let's call it, where zip code is not going to make sense as a numeric value, as too many distinct values, and it doesn't really mean anything statistically, right? Like if we look at zip code, I don't know why it didn't show up here, but the mean of zip code isn't going to mean anything. The median isn't going to mean anything. And it's not going to provide a lot of value here. So we may decide to remove it, or we may decide to just transform the value into less distinct value somehow. So experience, I'm going to query all experience values less than 0, just to kind of get a better idea of how I should tackle this problem. So I'm going to notice some immediate glaring things where I know it can't possibly be true that negative is a real number, right? So if I look at income, like there's a person at 25 years old, -1 experience, but they make $113,000 a year. They have a 4-person family. They carry a revolving credit card balance, and they're highly educated. There's no way that they have -1 experience. They make a good income, have a family. They're 25. So, if anything, maybe they're a year out of college. It should be 1, not -1. And I noticed looking at these values, all of the ages are low. The highest one I see here is this 28. And the experience negative is low. So I almost feel like they're all recent college grads who, though make significant income, some of them, some of them are lower. Might depend on what field they went in. Some of them have family already, so they're supporting a family. They're carrying a credit card average. So they had to be approved for a credit card by a bank. A lot of them have education and mortgages. They had to be approved for a mortgage. So you're starting to realize, in mortgage, we know you have to usually have pay stubs or significant, cash to get approved for a mortgage. The negative experience just doesn't add up. So I'm going to make a decision that this is a data entry error, right? So considering that, what would I do about it? Well, I'm going to make a decision by myself in this case, because I don't have a business person to talk to or be able to talk to the people who gave me this data. And I'm going to say I'm going to take the absolute value of this. So -1 is going to become 1, -2 will become 2, right? I'm going to take the absolute value of the experience field. Now, in a real world business scenario, you may want to do a little bit more as a data scientist than make your own decision. Like you may want to go investigate with your business team or your, if you have a data platform team, like, hey, is there a way we can determine why this value was negative at some part in the process? has it been negative since, like, was it accidentally negative from input, maybe from a survey to our actual customers, and they accidentally inputted a negative value. So you would actually want to work to understand why you have bad data and correct it as early in the business process as you could. So downstream, it's going to be higher quality, right? And that is what a good kind of process would be. In this case, when I'm doing a random data set from the internet, I can't do any of that. So I just have to make a decision how to deal with it. And here I'm going to apply a lambda function on the field that takes the absolute value of every piece of data in experience. So that will turn all values in experience to their positive equivalent. And I just ran that over the entire data set. Now I have 5,000 positive experience values. So great, that problem's fixed, at least for this data set. Now, zip codes is a new problem. And I know from my machine learning algorithm that too many distinct values of a categorical input, which zip code is, because I don't want to treat zip code as numeric, because the mean, median, and other statistical information of zip code as a number are completely meaningless, right? So we want to treat it as a string value. And string values in these classical machine learning algorithms are categorical, which means every string value is a distinct category, right, that categorizes that row of data. In this case, 467 is way too many categories. That's going to make the model potentially perform poorly. And so I need to reduce that complexity or eliminate it. So first, I'm going to take a pass at reducing it. Now, I know from some Googling that the zip code is actually a number composed of meaningful information. So the first digit is the national area of the United States. And the next two digits represent a sectional city or large post office. So that means the first three numbers of a zip code are a larger area that encompass multiple zip codes. And they are still meaningful from a logical standpoint. They still have meaning. So what I'm going to do is I'm going to reduce the complexity, the unique zip codes, by removing the last two digits. So here you see I have a Python function, and I'm returning the first three using a string splicing here in Python. The first three characters of the zip code indicate its large sectional center. And I'm going to create a new categorical column in my data set called zip section and apply the function over zip code. Right, and then I'm going to drop zip code because I no longer want it in my data set. So here we go. I've run that, and I've reduced 467 zip codes to 57 unique zip sections. Now, I still feel like 57 is a little high, but we're going to run with it for now because I'm really just trying to teach you about the process of transforming your data. So between zip code and experience, we've had to do two pre-processing steps to cleanse our data for the algorithm, right? And like I said, cleansing may happen here in Python code, or you may try and work with your data upstream to get better data, right? And these, you can take and expand this idea, how it would work for, if you had a team in your company implementing machine learning algorithms, that a large part of algorithm development and taking machine learnings and making them meaningful to your business is having good data to start with, right? That's very important to data science teams. So consider that a large amount of data science work is preparing data, and not just preparing one set of data. You may be preparing the platform of data as new data is generated, how it's organized, saved, etc. There could be a large amount of work there. But it's very important that data scientists have good quality of data to work with from the start, right? So if you're ever considering a data science type implementation or using machine learning, just expect that an early part of that project is going to be ensuring that your data platform and the data coming in is good data to work with. Now we're going to explore our data a little bit too. Just as a data scientist, I like to understand the meaning behind some of the data, to understand like what my data is telling me from just a visualization, like what I can understand as a person, right? Before I ask the machine to understand it as a machine. So I'm going to do a box plot against family and age. What this is telling me, if you can read box plots, is I have 4 box plots here. And for a family of 2 size, for example, I'm seeing about a mean age, let's say 45, right? And kind of the lower and upper percentiles are, let's say, I don't know, 35 to 56 or something. And of course, outliers and minimums take it down to that lower age range in the 20s and upper age range in the 60s. Now, what this is telling me overall, since these box plots are mostly similar, like they, of course, have some different means here, the quartiles are a little different, but overall, from a generic standpoint, the age and family distribution is pretty well even. So I have a really good diversity of age and family, right? And so that's just kind of good to know as you understand your data. I'm also going to look at income, because income can really tell us a lot about people's situation in regards to whether or not they'd want a loan or could qualify for a loan. So I'm going to look at income versus credit card average. And so I'm trying to see if I can visually determine a correlation between these two. Now, looking at this graph, as income increases, I'm seeing a positive slope to credit card average. And I also see on the line graph this shaded area. That's kind of, the actual line is like the mean or median. The shaded area is like the spectrum of values that it could be in. But in general, I'm seeing a positive increasing slope. It's mostly linear, I would say. And it's indicating that as income goes up, credit card average goes up. That makes sense, as people who make more money will carry a higher revolving balance because they're just spending more every month, right? And maybe they're paying off their balance every month. Maybe they're running a high average and, paying that interest. We don't really know that. We just know on average that they're spending more, holding a higher revolving balance for whatever reason it may be, right? And, something when you think about that towards the business case of a personal loan, like if you utilize as a person too much of your credit, you may be less likely to be able to apply for a loan, especially as your income goes lower, right? Because it's like a debt to income ratio that loans take. So if you go extreme on the ratio, depending on if it's income or credit card average, that either increases or decreases your factor in loan approval, right? Which is going to ultimately determine the target that we're looking for. I'm also going to look at income to mortgage. And unsurprisingly here, I see a similar trend. Now, I had to plot this as a scatter plot because I knew and wanted to see all the 0 values here. And you see a lot of them are 0 everywhere from income, from very little income to a ton of income. We see 0 values. And again, we don't know if these are renters or if they are people who own their home outright without a mortgage. We just don't know. But then we do see a positive correlation. And again, a positive correlation is just when the graph goes up and to the right between income and mortgage. And that a mortgage is a type of loan. And we know in mortgages, the more money you make, the higher mortgage you can qualify for. Notice, though, we see a very definitive maximum line, linear line. So you can tell it's almost like a linear qualification process. You can also see that, as income goes up, though, it's just all over the place. Now, they could have gotten a cheap house, or they could be far along in comparing their or paying off their mortgage. We could maybe do some kind of 3D plot with age here to even determine more of that. So you could see how you could really just dive into understanding your data, right? And it's important as a data scientist that you have some good foundational understandings of the data you are working with, and that kind of you check your assumptions and ensure that you really understand what's going on, from a high level statistical point of view, because you may be asked about this or have to use your understanding of the data to make sense of the outcome that we're going to get. Now, I want to see how zip sections really played into determining like these unique values. Like, what did it mean that I did this? So I did a count plot. I noticed that some zip sections have a lot of customers. And, this could be for many reasons. Like the bank could have more branches in that area. or maybe the type of customer, happens to live in that area that the bank is marketing to. And I don't, the bank is called Bank. It's obviously an abstract data set. I don't really have an understanding though. Is this a regional bank? Is this a national bank? I don't know. Obviously though, if I worked for the company, I would know. But as you can see though, there, some zip sections have very little customers, so very little data points, and some have a lot. Now, I'll be honest with you, this to me is a sign that I really just should remove zip section from the algorithm. But for the sake of learning some things later on, I'm going to leave it in. And we'll get to why I do that later, because I want to show you how leaving this in is going to affect the machine learning model. But another interesting thing I can look at in zip section is zip section against income, right? And as you know, in different zip codes, there could be different, types of, maybe inner city with people who have, jobs downtown. They may naturally have higher income than people out in rural areas, is one way to simplify that. So I'm looking at zip section versus income. And you can see actually like zip section 918, wherever that is in this country, they have potentially super high income. I don't know. I think 9 is maybe California. Maybe that's like San Francisco or LA or something, like deep urban area where you're going to see kind of those high cost of living type incomes reported for this bank. And then, but, other than that, most of these seem reasonably well distributed here in this middle income range. There's one that's kind of low down here, but again, we had very little input. So like this data is in a way biased because there's not enough data. So it's hard to really draw a meaningful conclusion, especially for the zip sections that don't have high counts, right? So like for the 918, which had this very high income, let's see, we had 918, we had almost no data. So we could have like 4 customers there who have super high income, so even that could be telling us almost nothing, right? It could be a rich rancher. It could be a rich person in the middle of the city. I have no idea, right? I could Google that zip section, I suppose, but the machine learning model certainly doesn't know, so it's kind of meaningless. And that speaks to, again, that I'm not sure that this is a great feature for the machine learning model. A pair plot is just a way to plot a ton of stuff at once. In fact, it may take a few seconds to run. But it's a way to, at a very high level, do a bunch of graphs on a bunch of data sets. In fact, it's taking a few seconds to run for the rest because it's generating like, 20 graphs. Here they are. So it plots every parameter except some that I've removed against every other parameter. You can see sometimes you can draw meaning from this at a high level. Sometimes you can't. I see some of the things already graphed, like income to mortgage. But also, like, here's mortgage to experience, mortgage to age. I don't see any meaningful at high level from the graphs there. It's kind of scattered information. So we're going to move on. Now, the heat map is interesting. So the heat map is going to generate a heat map where we have high correlating values within our data. This is taking a second to run. It's crunching a bunch of numbers. But it's going to look for correlated data. Here we go. Here's the heat map. So let's look for something with high correlation.
Alrighty, guys. It looks like we lost Michael. I thought that was actually my internet going bad. Hold up for a second. I will attempt to message him. There you are. You're back.
Okay. I must have had dropped for a second. Let me get back up to sharing.
Yeah, I called up the internet burping because it ate all the packets. I thought that was my connection at first, and then you dropped them. It had to be you. Yeah.
I love it.
All right, there we go. We're looking at your heat map.
Great. See, as I was saying, the heat map is drawing a view for me for correlations. So positive correlation is a number closer to 1. So like this 0.6 income to education. And I have credit card average to family, or no, to income. So we actually already knew that correlation from looking at a graph. This means that the numbers are correlated. And a positive correlation will mean a higher credit card average will correlate by a ratio of 0.6 to a higher income. Now, a negative correlation will just means the slope of the graph will be negative, right? And like if I look for one, Well, it's not really a high correlation, but education to experience negative 0.1 is barely a correlation, but that just means as education increases, income decreases, which of course doesn't make sense at all. But also negative 0.18 is basically no correlation. So that's not even, it's so close to zero. Zero basically means no correlation. I was just trying to find an example. But if you had something closer to like negative 0.5, that's at least starting to indicate correlation, which we don't see for negative, but we do see for positive. Looking at, I wrote down some of my observations. Now, if you're, a data scientist working for a client or for a business, you're probably going to make like a presentation that describes a lot of your findings, your process, and you're going to present that to your stakeholders so they have confidence in what you're doing. So you bring them along with the journey of your understanding of the data set and how you're going to give some results for this, for this function you're performing, analyzing this data. And so I've written down just in bullet points some of my observations, but just think, you want to bring your stakeholders along in the journey of understanding the data, the input, the outputs, just like you're as a data scientist doing, because you want them to learn with you about this data and build confidence in your process for ultimately the results you're going to give, right? And so in that presentation, right, you would give all your observations about the input data. And of course, we're going to add to it as we build our model. So data preparation. Now we're actually getting into the machine learning. Isn't this fun? Okay. And this is like, I'm 40 minutes into my presentation. I've done a lot of data preparation. That's data science for you. All right, just to give you a feeling. So I'm gonna start preparing my data to build a model. I'm gonna run this function called get dummies. This is gonna perform a technique called one-hot encoding. That's where it has to build a feature parameter for every categorical value. And you see, I'm going to have the number of zip sections as they are distinct. And that is because that is how you input categorical values into a machine learning algorithm. For some of these others, which are binary, they only need one because 0 will mean yes and 1 will mean known. Whereas for multi-categorical values, I need 1 per distinct value. Right. This is so I can make sure I display lots of I'm gonna kind of show you what that looked like from a data section. Let me find, so zip section 926, 1 means yes, this row data had that, and the rest of those zip sections will be 0. And that's what one-hot encoding did. And you can see though how it greatly expanded the input into the machine learning model. This makes models more complicated, right? And you generally want to be very mindful. There's not like there's a, like stay below this number type of advice, but more just mindfulness of how many parameters you put into machine learning models, right? Now I'm going to separate my data into, if I had 5,000 rows, I'm going to take 20% of those, see test size 0.2. I'm going to withhold 20% to test the output of my model to determine how good the model is performing, which means the other 80% are going to be for training. And that's what this is doing. I have a training set and a test set. And something I did, by the way, I forgot to maybe say, is I separated this between these X and Y variables. So the Y variable is my target variable. You see I extracted personal loan from the data set. And my X variable, I abstracted everything except for personal loan in the data set. So X is everything except personal loan and Y is personal loan. Right? And that's because Y is my target. And so here I have my sets of X and Ys. And then I am going to kind of print that out. Now, something to note is it's good to know your ratio of data. So in my training set, for example, I have 3,616 no values, like they did not obtain a personal loan, and 384 yes values. And the ratio is right here, 0.9 to 0.09. Now, for a lot of machine learning models, this may be an issue, an imbalance. It's called a class imbalance. And I actually may use statistical techniques to decrease this class imbalance. Like I may create dummy values, let's call it, or let's call like statistically correlated values that are very close to the yeses and input more of them, just so that there's more reinforcement of the yes values. That's actually what this commented code did up here. I must have it commented because something went wrong. So it's commented out. I'm not going to try and, wing it right now. So that's looking at our class imbalance. I think for the algorithm we're using, which is a decision tree, this won't matter as much, but it's so imbalanced, it kind of is a concern. So that's something machine learning engineer just needs to be aware of and may need to account for in this process.
If I could interject with a question of my own.
All right.
Also, I believe it would be a problem if your test data had a much different ratio than your training data.
Oh, I'm so glad you brought that up, because I actually did account for that. This stratified parameter that says yes, that actually says stratify the splitting of the yes and no values in an equal ratio between the test and the trained data set. So you'll notice I printed out the ratios. The test and train have the same ratio. Now, if I didn't do this, in fact, I can just show you, and I can set that to no. I can run it. Oh, n is not defined. Well, maybe I just take it away. Cool, it ran, and let me print these out. Now you can see the ratios are different. 0.9 and 0.1, 0.905, 0.095. Actually, they're very close, but they're different, right? And so stratify keeps the ratios the same. That was a great interjection there. Thank you. Cool, now they're back to normal. So now I wrote a bunch of Python code, and I'll go through each of these quickly. But these are helpful functions for model performance analysis. So these functions help me analyze my model performance. That's it. So I'm going to print a confusion matrix, and I'll explain that later. I'm going to get different scores of a model, and the scores are accuracy, recall, precision, F1, and ROCOC. I'll explain each of those as we get to them. And I have a function of print the tree. That'll be a cool thing. And then get importances will actually tell me what inputs were important to the decision tree, right? Because some features are going to be determined to be more important than others. And I'm going to be able to what's called the precision recall curve and the ROCOC. And so these are just some helpful functions to let me visualize the results. Now I'm going to actually finally do the machine learning. And here we go. It is 4 lines of code. It could have been 2 lines of code. But I call tree basic equals decision tree classifier, and I fit it to the training data set. That's it. So simple. Machine learning done. Woohoo. So let's go ahead and look at the model. Now, looking at the decision tree, I have what's called the decision tree confusion matrix. So if you think about predicting values, you predicted yes, and they are yes. That's this bottom right. But then you have predicted yes, and actually it was no. That's this left side right here. And then you predicted no, and it was no, top left, and predicted yes, but it was no, top right there. So you have 4 different types of answers on whether a prediction was right, which is 2 different types, and how a prediction was wrong. There's 2 ways you can be wrong, right? And the different ways are called your type 1 and your type 2 error, whether or not it's a false positive or a false negative, right? And that is important to note on how you can optimize in which way you're wrong, because if you're going to be wrong, it may matter how you're wrong, funny enough, and that can actually matter a lot. So we're going to look at the scores here. Now, a 1.0 on my training set means, well, of course, my decision tree is perfect on the data I trained it with, and on my test set, it is not perfect. That's, of course, expected. It would not be perfect on the test. It's actually a little bit of a warning sign, though, that it's perfect on my training set. Usually, you'd expect some variation because, the randomness in training it. And that may mean that really my model's not fit very well. I'm going to talk about some of these accuracy or these metrics. So accuracy is just how often am I right? Now that actually in this data set is a bad metric because 90% of my values are no. That means no matter what, 90% of the time I'm going to be right, right? It's almost like the minimum possible accuracy is 90.9. It could not go lower just because of the imbalance of values. So in a lot of data sets, accuracy is actually not the greatest metric. It needs to be considered, of course, but it has to usually be considered with other metrics as well. So your precision is a fractional ratio of your true positives over true positives plus false positives. So less false positives make higher precision, which means less you predicted positive and it's false. And recall is the opposite, less false negatives. Now, if you think about it, this could really matter, right? Let's say you're diagnosing if someone is sick with a bad disease, and the result of your diagnosis is just that they have to take a more advanced, expensive test to see if they really have it. But this is like your quick test, like, hey, we give this to everyone just to see if they go the next test. You actually want to have less false negatives because you would rather have false positives. You'd rather send more people to get the better test to be more sure they don't have the disease. So you would actually optimize to have less false negatives, which means you want it on the bottom of the equation, which means you want a higher recall, right? And so this is actually a business decision in classification algorithms if you optimize for recall or precision, right? This is a conversation that should absolutely be had with your business team. You should be able to explain the concept of optimizing for when the prediction is wrong, because there may be a preference to why you're wrong, right? And I'm running short in time, so I'm going to kind of skip some of this stuff. I'm going to print the decision tree. Now, what this is cool, this is when you get into this concept called explainable AI that people talk about. Like, can you explain why your artificial intelligence made the decision? And in the case of a decision tree, you can. I can, on a poster board even, literally print out the tree of decisions that were made to get to a yes or no. Now, for this tree, that tree is ugly. And, you know, you can see it starts with if income is less than 104, it goes to the left. If it's greater than, it's going to go to the right. And it makes a ton of decisions until it gets to a yes or no, you know, at the nodes. Now, overall, this is way too complicated. I want to see a simpler tree. Additionally, I see that my importances of features, and you see I'm using those functions, income, education, family are very important, but then it took into consideration way too many random zip sections. I don't like that. So I'm going to use a technique called pre-pruning a decision tree. And this is where you start getting a little bit more complex machine learning code. I'm going to prune leaves off the tree as it's being made to be a simpler tree in hopes that it actually makes it a better tree. I'm going to go and run that. So what this is doing is I'm optimizing the hyperparameters, if you remember from my deck earlier, into a bunch of possible values. And I'm going to do an exhaustive search over all the combinations of these hyperparameters to see which give me the best decision tree looking at what's called the F1 score. I didn't talk about it, but the F1 score is basically if precision and recall are competing values, like as precision goes up, recall goes down. An S1 score is when those meet in the middle and you have the highest possible precision and recall, which means they won't be the highest individually, but it's when they're highest as a group, which basically means I don't care about optimizing precision or recall. I want the best of both, right? Which means you're not going to get the absolute best of either, but you will get the best of both as a pair, right? Now, I'm just doing that in this problem to show you different techniques you can do. Now, it took me 24 seconds to do that exhaustive search for the best decision tree. You could imagine if I had a data set instead of 5,000, it was 5 million. And I had even more hyperparameters. This could take hours or days. This is where you may want compute clusters. Fun. All right, we're going to scroll down. A bunch of them failed to even generate a tree. That's okay. But it did finally find a decision tree, and it gave me all of the hyperparameters. So I'm going to go ahead and print out all the information about that tree. Now I'm seeing the basic tree, and I don't know why I didn't print out the word basic, but these top two train tests are my basic tree. The bottom two are my pre-prune. And essentially my pre-prune, let's look, the accuracy is better on the test set. The recall is much better, went from 0.87 to 0.93. The precision is also much better, 0.89 to 0.96, and the F1 is much better, 0.88 to 0.95. And the raw calc also increased, right? Additionally, my training set isn't perfect anymore. This is actually indicating I have better randomness in the tree, and it's not going to be perfect on the training set my data. So overall, I created a massively better algorithm by machine learning algorithm by hypertuning my parameters. So this any algorithm optimization is a very important step in model development, right? So I chose a machine learning algorithm. I chose to make a decision tree. I fit like my base case, which is kind of like your baseline. And then I'm going to optimize. I'm going to tune the algorithm until it's a better version of the baseline and compare it, right? And I may do a lot of iterations of tuning, right? In this case, I'm going to do one more. Oh, first, actually, I'm going to look at the importances of my pre-pruned tree. Now I see a way better results. I see that there's only 1, 2, 3, 4, 5, 6 features that are important at all in the tree. That is really cool. Now, if I print the tree out, that means it's going to be a simple tree. And it is. Look at this tree. It's beautiful. It starts with income less than or equal to 116,000 goes to the left, and greater than it goes to the right. And then you can see where it makes the decisions. The next decision going right is if education is greater than 1.5, it's going to true. If they have income over 116 and an education greater than 1, they are highly likely to take the loan. That's cool. I can actually give this decision matrix, the whole tree, to my marketing department. They can apply the tree even manually, like per customer, or of course we would do it programmatically. Obviously, we're software development. And we would apply this decision making over our targeting. And if it mattered, if there were like government regulations or we just wanted transparency, we could show how we made our decisions if we were ever audited about the why of our decision making. The reason that's important is because in some cases, it is important to understand the why, right? Either due to regulations, due to transparency. You also may want to make sure that you're not introducing like social biases, right? Like you're not using parameters or have heavy dependence on parameters that indicate like protected classes, by government regulations or anything like that. And you would want to have that level of transparency and openness in how this is done. That could be very important. And that's a whole topic about like unbiased machine learning algorithms, or at least low, diminishing biases as much as possible, right? Because you can't have perfectly unbiased algorithms, maybe, because you're in the end, you're always using historical data to predict the future. So in some level, there is some historical bias to your future predictions, right? Like it's unavoidable. Oh, look, my automated ML job finished. Cool. I'm going to run over there now. Let's maybe refresh this page. And I have 1 minute. Boom, I'm completed. And I'm going to go look at the metrics. Look at that. Let's look at the F1 score, 0.96. And my F1 score up here was 0.95. So the machine built barely a better machine learning model than I did. But that's actually kind of the joke of the presentation is, the computational power of clusters, and it tested, 100 different machine learning algorithms. I only built one, and it built a better model. So that's my presentation today. Again, please connect with me on LinkedIn. Feel free to send me messages and ask me questions, or if you just want to connect and talk about data science or improving, love to connect with you.
All right, and this is the last call for any questions. And it looks like we don't have any. So, hey, you made a perfect presentation.
Yes.
Perfectly understandable to everyone.
All right. Thank you, everyone, and see you around.
Have a great day, everyone.